We are back. I've been disturbed by this device. I've been disturbed a lot. But here I am. Sorry for that. For that disruption. I was saying that a colligative property depends on the number of particles which you have put in a solvent. And this is the example which I was giving. For example, if one dissolves salt in water, one is interested in knowing how many particles, how many grams of salt have been added to this water, but not the nature of that salt. We can look at a variety of salts. Yeah. So these are properties which investigate or interested. They depend on, their variation should depend on the particles of salt which you have put in water. What are the examples? The examples are there. You have vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. So we start with vapor pressure lowering. What is this? Now, for vapor pressure lowering, we consider what happens when what? When a non-volatile solute is added to a solvent. By the way, there are some assumptions onto which these properties are valid. Hope the teachers gave you those assumptions in class. Yeah. Now, we do not consider any solute. Particularly, for example, in the previous slide, I have said that you consider what happens. Those are properties that investigate the number of salt. How many grams of salt have you dissolved in this water? But we do not just consider any solute. The solute to be considered should be non-volatile. Hope you know what I mean by a non-volatile solute. A volatile solute, think about, do you know this thing, this spirit? Spirit is volatile. Why? It has a high vapor pressure, it has a low boiling point. Those are key components of volatile solutes. High vapor pressure, low boiling point. As in, if you have ever interacted with the spirit, it easily evaporates, it easily spreads. So that is a volatile solute. So for solutes that are considered here, they should be non-volatile. So those spirit examples, spirit cannot work now in this case. So when a non-volatile solute is added to a solvent, fewer solute molecules escape into vapor phase and vapor pressure decreases. What are we trying to say here? If you add salt, if you add, what vapor pressure lowering says, if you add salt to water, we have this. So what is vapor pressure? By the way, you have to first understand what these terms mean. What is vapor pressure? Just as the name sounds, vapor pressure is pressure of vapor. Pressure of vapor. For example, if you boil water, that vapor that comes off from that water, it exerts pressure onto the water surface. If you have your reservoir here and it has water, if you boil this water, if you heat this water, there's vapor that comes off from that water. Now there's vapor that comes off from the surface of this water. Now this vapor, which I am abbreviating as VP, that vapor exerts pressure onto the water surface. That is vapor pressure. Yes, the pressure exerted by vapor. So what are we trying to say here? If you add a solute, for example, salt to water, and you boil this solution, now since the effect, this is the effect of adding a solute onto vapor pressure. If you add the salt to water and you boil, fewer solvent molecules. If this water now is containing salt, fewer water molecules will evaporate from that solution. fewer water molecules. If that water now is having salt, if water is having salt, fewer water molecules will escape or evaporate from that solution. Therefore, vapor pressure decreases. That is the effect. The effect of adding salt to a solvent on vapor pressure. Once you add a solute to a solvent, I have considered two cases. Look at the case where water is not being mixed with salt, and another case where water is being mixed with salt. For the case where water is being mixed with salt, after making that mixture and you boil it, you'll have fewer water molecules that will escape. Do you know why? If you add salt to water, some salt particles will occupy the surface of this solution, some salt particles, therefore reducing the escaping tendency of solvent molecules into vapor phase. And Raoult was able to investigate that, and he summarized it in this relation. Now, this is a brief. I assume that your teachers have explored the applications of that calculation. Of this what applications of this law, particularly in vapor pressure law. I think there's that one of ideal solution. Then the other property is the boiling point elevation. What is the effect of adding a solute to a solvent? Adding a solute increases boiling point of a solvent. This is what we should expect. If you add salt to water, if you add a solute, as in, think about these two situations. You have water, which is not mixed with anything, and water which is mixed with the, say, sand. You expect the other water, which is not mixed with sand, to boil faster. However, if you now add something to that water, it's like you'll be boiling two things. That is, if you want to understand it in a basic way, you'll be boiling water. On top of boiling water, now you are also boiling salt. That's why this is called boiling point elevation. Boiling point has to increase. So adding a solute to a solvent increases boiling point. Yeah, and this is summarized by this relation, where change in T is the boiling point elevation, Kb is the embryoscopic constant, M is molarity, not molarity. This is molarity. Yeah, molarity investigates. I think molarity investigates the amount in grams or kilograms. Example: salt added to water increases its boiling point. Then the other thing which I can comment on is the freezing point depression. What happens to freezing point? If you add a solute to a solvent, the freezing point of a solvent is lowered. The freezing point of a solvent is lowered. For example, these are some of the key cases: salting ice rods, and antifreeze in car radiators. So addition of a solute, the key takeaway is that addition of a solute to a solvent lowers its freezing point, the rate at which it freezes. And still we have this relation which summarizes the key takeaways, where change in T is the freezing point depression, Kf is the cryoscopic constant, M is the molarity. Yeah, now this is applied in calculations. Then finally, osmotic pressure. Osmotic pressure also follows this relation there, where pi is the osmotic pressure of the solution, M is the molarity, R is the gas constant, molar gas constant is the temperature in Kelvin. Applications: water purification, biological systems. Yeah, so what are the key takeaways? Below is the table which summarizes those. Vapor pressure decreases, boiling point increases. Okay, we look at what happens if a solute is added to a solvent. Yeah, if you add a solute to a solvent, how will the vapor pressure change? How will the boiling point change? How will the freezing point change? How will the osmotic pressure change? So vapor pressure will decrease, boiling point will increase, freezing point will decrease, and osmotic pressure will increase. And similarly, I still have another tuition here. There you are. Initially, we are looking at effect of adding. I have said we are looking at effect of adding a solute onto a solvent. So initially, you see, now let us start with boiling point elevation. Hope you can see where my cursor is for boiling point elevation. Initially, we have this case. We have the case where the solvent is alone. Hope you are seeing where my cursor is. The temperature, the boiling point of a solvent when the solvent is alone. You see, now if you add a solute, that boiling point increases. So you have elevation in boiling point. Why? Because addition of a solute to a solvent is like you'll be boiling two things. You require to break the forces of attraction within the solvent. You also require to break the forces of attraction within the solute. Therefore, boiling point has to increase. Then for freezing point, initially the freezing point is high. Now you can look at what? You can look at water without impurities. Initially, you have water without impurities. Water without impurities freezes at 0 degrees centigrade. So initially, it is at 0 degrees centigrade. However, if you add some impurities to that water, the freezing point will further decrease to negatives. If initially it is at 0 degrees centigrade, then it will further decrease to 10 degrees centigrade. Why? Because now you also need to freeze. You also need to cause freezing of those impurities that are there. So therefore, freezing point has to decrease. Vapor pressure, initially this is what you have. This is what you have. The pure solvent easily escapes when you boil it. It easily escapes. That is if it's not mixed with anything. The solvent molecules easily escape from the solution so that the vapor which is obtained exerts vapor. However, if you add a solute to that solvent, like here now, are you seeing those dots in? I think that is color green. You will lower the escaping tendency. You lower the escaping tendency of solvent molecules. Why? These particles which you have added to the solvent, they occupy surface of the liquid, reducing that escaping tendency, thereby lowering vapor pressure. Then osmotic pressure also as well decreases. When you try to investigate the. However, this most applies for biological systems. Yeah, it most applies for biological systems.